So today I'm here to present SynthCT towards portable constant code. This was the work that I did with my collaborators at UIUC, Grant, who was an undergrad there, and my advisor, Chris Fletcher. So microarchitectural side channel attacks break software security guarantees and leak private information from software. And over the past few years, a variety of these attacks have been developed that break different shared hardware resources. But for this talk, I want to focus our attention on a small subset of these attacks that exploit the differences in execution time of a single instruction based on its operand values. A familiar example that many of you may have seen are cache-based side channel attacks. Consider this move instruction here that accesses a memory address that is derived from a secret, like a cryptographic key. When relevant data is fetched from memory, intermediate microarchitectural states, such as the cache hierarchy, is updated as a function of the secret value. And now if an attacker can observe this cache state, either directly or indirectly after such a memory access, then they could learn the values of secret data. Another less common example are variable timing instructions, like, for example, the floating point instruction from x86. Depending on if the operands of this instruction are in the subnormal range or not, the instruction takes either a fast or a slow path. And if an attacker is able to observe this difference in timings, they could learn something about the secret value. Now, prior work has shown that just observing this difference in timing is sufficient to break security guarantees implemented in our browsers today. In this talk, I will refer to instructions that have this operand-dependent variable timing as unsafe instructions, while instructions that do not such variability in timing as safe instructions. So constant-time programming is a holistic software-only defense against such side channel attacks. Today, when experts think about writing constant-time code, they mainly follow these three following rules. First, to prevent leaks through branch side channels, they do not use secret data as predicate to branches. Second, to prevent secrets leaking through cache-based side channels, they do not perform any secret-dependent memory accesses. And lastly, they do not use secret data as operands to variable timing instructions like the floating point or the divide. I will refer to a program being mostly constant time if the program is free from the first two kinds of leaks, that is either through the branch or the cache-based side channel attacks, where it may have the third kind of leak. But this simplistic view of constant-time code and microarchitectures is actually insufficient to have strong security guarantees in practice today. So here in this table, I have a list of different classes of instructions as rows, and as columns, I have different microarchitectures. A check mark represents that an instruction is believed to be safe, while an X denotes that an instruction is safe on a microarchitecture, unsafe on a particular microarchitecture. So from a previous slide, this is what the current expert constant-time programmers believe. They believe that all simple bitwise operations and instructions like multiply are safe on all microarchitectures, while the first four categories of instructions, that includes the branch, the memory accesses, and the divide and floating point are all unsafe. But actually, there are many different microarchitectures in practice. Each may have its own set of safe and unsafe instructions. For example, in the second microarchitecture B here, it may turn out that the multiply instruction is unsafe, maybe due to a newly implemented optimization like a zero-skip multiply. Similarly, a subset of bitwise operations may also end up being unsafe, depending on how they're actually implemented in hardware. On the other hand, we may have microarchitectures such as C here, where floating point and divide are actually implemented in a constant-time way, thereby making their use of secret data actually safe. So when we take a program that was originally written for this microarchitecture A and later run on this new microarchitecture B, it leads to security vulnerability as the multiply instruction will now leak its secret values. This is a security gap with the current constant-time code. On the flip side, if you take the program that was written for A and later run it on this new microarchitecture C, it does not lead to security vulnerability, but leads to a performance gap, mainly because you could use better performing instructions like floating point or divide rather than emulating them in a constant way in software. So this is the performance gap. The goal of this work is to take mostly constant code that was written for one microarchitecture and a safe set in mind, and automatically transform it to be safe to run on another microarchitecture that may have a very different set of safe instructions, thereby bridging this performance and the security gap. Before we dive into details, I want to give you a quick high-level view of SynthCT. So our framework takes as input mostly constant code, a microarchitecture specification that divides the instruction ISA into a safe and an unsafe set. Ideally, we would get these specifications from hardware vendors, for example, like ARM's DIT, or they may be reverse engineered by the community. And lastly, an ISA specification that defines the functional semantics for each instruction in the ISA. In our work, we use the most complete set of x86 semantics written in prior work. Just to give you a sense of what the semantics look like, on the slide, I have the semantics for the add with carry instruction from x86. I don't need you to focus on the details, but what I just want to highlight is that each instruction semantics is an abstract syntax tree. where every node in the tree is an opcode in the K language. So SynthCT takes these three as input, and using program synthesis generates a synthesized library of translations, where each instruction that was unsafe in the original security specification has a corresponding translation that uses only the set of safe instructions for that microarchitecture. Later, this synthesized library of translations may be used as a part of the compiler backend or a post-compilation binary rewriting step to harden mostly consonant code to a target-specific microarchitecture by replacing every unsafe instruction by the corresponding translations. So now we'll focus on how to build the centerpiece, which is the brain in this picture. We formulate the problem of generating a set of safe translations as a program synthesis problem using counterexample guided inductive synthesis, or CGIS for short. So here, in this example, we want to synthesize the translation for the add with carry instruction that I showed you on the previous slide. We pass the instruction semantics to our synthesis task, which is currently implemented in Rosette, along with the translation length, that is maximum length of the program we want to synthesize, and the set of instructions that are allowed to be used while generating these translations. We also call this components. The output of the synthesis task is a synthesized translation that is semantically equivalent to our input add with carry instruction. Now we repeat this process for every unsafe instruction in the ISA to generate a synthesized library of translations. However, we quickly run into scalability issue when we try to synthesize an ISA like x86-64. So in our experiment, we actually found that the synthesis time is exponential in both the translation length and the allowed set of components to be used. So in the rest of this talk, I'll go over techniques that we implement in SynthCT to make the synthesis problem tractable for a ISA as complex and large as x86-64. All right, so after the quick break, now we're going to focus on how to deal with this scalability issue that we face with synthesis. Okay, so from our experiment, it was clear that we could not use the entire ISA as a set of components for instructions to synthesize. So to reduce the synthesis time, we need to bias the synthesis search space to some smaller space that is more likely to implement our target unsafe instruction. But we need to be careful when selecting the subset of components, as if we select a bad set of components, we may lose out on potential translations. Or even worse, we may not find any translation that is semantically equivalent to our unsafe instruction. So our key insight here is that we can use structural similarity between the ASTs of instructions to estimate how likely an instruction is useful in the synthesis of translation of an unsafe instruction. To illustrate this idea, here is the semantics for add with carry that we saw from one of our previous slides. If we compare this AST for add with carry with an AST for subtract with borrow, we see that there's actually a large overlap between the structure. The only difference is in the highlighted nodes here. A subtraction is just addition with negation. The subtract with borrow uses a negated version of the first operand, while the add with carry uses the first operand directly. And indeed, if we give the right set of components to our synthesis task, where we get back the synthesis solution that implements add with carry using subtract with borrow, subtract, and a move instruction, all of which share a high similarity with our input add with carry instruction. So using this intuition, we build our component selector strategy that returns a set of most similar components for the target instruction we want to synthesize. So we start with the ASA semantics for all instructions in the ISA and pass it through graph to vec to generate a fixed length vector embedding for every instruction. Then we take the query instruction we want to synthesize, get its corresponding vector representation, and do k nearest neighbor search to get a ranked list of components. We take our top n of this and use it as our components for our synthesis task. In our experiments, we selected this number to be about 32 components. Now I'll quickly describe the other two techniques we develop in SynthCT to address the remaining synthesis challenges. So our component selection strategy exploits structural similarity between instructions to estimate the usefulness in synthesis. But sometimes there may be complex K opcodes that hide such structural similarity between instructions. For example, take the AST for the rotate left instruction here that uses the ROL opcode. Just by looking at this AST, it's hard to find out that this instruction is actually similar to a shift left instruction. If you think about it, a rotate is a shift plus a bunch of bitwise operations. But looking at this AST, it doesn't tell us that. So to help component selection, we split such complex K opcodes into simpler opcodes. Here, the ROL opcode that you saw previously is replaced by this larger subtree, which is semantically equivalent to the rotate, but uses simpler operations. Now, the node splitting rules are expert written and ISA independent, and we currently only use this for a handful of instructions. This may be expanded in the future to support more complex instructions like floating point. Next, to synthesize complex instructions that need, okay, it's not working again. Okay, yeah. Next, to synthesize complex instruction that may need very large translation lengths, we develop instruction factorization. This is a divide and conquer solution that tries to synthesize parts of the AST in isolation and combine the solutions to form the solution for the larger instruction. So here is an example of a large AST of leading zero count, and I will zoom into the very top here and simplify it to give you a view. So rather than trying to synthesize that large complex AST that you saw earlier, we want to synthesize smaller subparts of the AST that we call factors. So here in this example, we start considering smaller parts of the AST. So first we consider this factor F1, and then we consider this factor F2. So we synthesize these subtrees in isolation. Once we have the solutions for F1 and F2, we go up to its parent, which is the factor F3, and we synthesize F3 using the solutions for F1 and F2. Similarly, we build up the solutions for F4 and F5, and once you have the solutions for F3, F4, and F5, we use these solutions to generate the translation for the original large complex instruction. So instruction factorization allows us to synthesize many short translations and then combine the solutions together to form the solution for a very large complex instruction that may need a large translation length. Putting all of this together, we first start with the semantics for all instructions in the ISA. If an instruction contains any complex intermediate K opcode, we use expert-written node splitting rules to simplify such opcodes and update the AST. Next, we check if the instruction is large and complex, and if it is, we use factorization to break it down into multiple subtasks, synthesis subtasks. Then, we want to synthesize either the instruction or its factors iteratively. And to do that, we first do component selection to get a rank list of components. Then we take the instruction semantics and the set of components and pass it to a synthesis task, which gives us a synthesized program. This process is repeated for each unsafe instruction in the ISA to get a synthesized library of translation. So to summarize this technical depth of this talk, I'm just going to highlight these three key takeaways. So if you forget the rest of it, these are three most important points. In all the techniques that we introduce, we try to exploit the structural semantics to make synthesis problem tractable. We first exploit structure and component selection strategy to bias the synthesis search space and cut down the synthesis time. Then, if the instruction is large and complex and needs a large translation length, we once again use a structure to synthesize parts of the ASTs in isolation and combine the solutions. And lastly, when structural information is insufficient to exploit the above two strategies due to complex K opcodes, we use expert-written rules to split such nodes into simpler opcodes. And this is done in an ISA agnostic way. Next, I'll go over to the evaluation. In the evaluation, we want to answer two main questions. First, how powerful are SynthCT translations? As this is the first of its kind tool, we first need to develop an evaluation methodology to answer this question. And we also want to do this in a microarchitecture and a safe set agnostic way, as today we do not have vendor-provided safe sets to compare our solution to. Second, how scalable is SynthCT to complex x86 instructions? So in the paper, we actually demonstrate two case studies to synthesize complex x86 instructions. For example, the divide instruction that is believed to be unsafe on microarchitectures today. But in this talk, I'll focus on answering the first question, that is how powerful are SynthCT synthesized translation, and I'll leave the case studies for you to read in the paper. Intuitively, our translations are more powerful if they're able to support a variety of microarchitectures with many different safe sets. Therefore, the synthesized translations should implement a large part of the ISA using a small, simple core set of x86 instructions. So rather than starting from an assumed safe set, we try to synthesize translations for every instruction ISA, assuming that any of them may turn out to be unsafe on a target microarchitecture. Then once we have the set of synthesized translations, we ask the question, given this set of translations, what is the minimal number of instructions that are needed to implement the entire ISA? So to help with this analysis, we build an abstraction of a synthesis graph. In this graph, every node is an ISA instruction, and an edge from instruction I to J represents that instruction I uses J in one of its translations. Here is a synthesis graph from one of our earlier runs, and as it turns out, it can be very large and complex. So I'm going to simplify it a little bit to show you how we go about getting these minimal safe sets. So given this synthesis graph that is simplified on this slide here, how do we generate the minimal set of instructions needed for the ISA? Once again, the nodes in this graph are instructions, and edges represent instruction use in a translation. We need to find the minimal set of instructions needed to implement the full ISA, that is instructions A through G in this example. So clearly, we need to include the nodes that are leaves of this graph, as they don't have any translations, and they cannot be written in terms of any other instructions. So I will call this a core safe set, and in this example, instruction C, E, and G form the core safe set. Next, we have a loop in this graph where instruction B uses E and vice versa. These loops represent choices. That is either B or E, but not necessarily both need to be part of the safe set. And I will call this the augmented safe set. So using this concept of core and augmented safe set, we can generate not just one, but many different concrete safe sets. So in this example, there are two such concrete safe sets, CFGB and CFGE. As you can see, both of these are minimal. That is, they can be used to implement the entire ISA, but removing any instruction from either of these sets means that there's at least one instruction we cannot implement using the safe set. We do a similar analysis on the large original synthesis graph that I showed you earlier, and here are our results. Our unsafe set contains about 275 instructions, which forms 75% of the ISA. So these are the instructions that we have translations for using a set of safe instructions. Then right here, we have the core safe set, which contains about 54 instructions. Just to give you a flavor of what goes into this core safe set, it contains some bit counting instructions, some rotates, some shifts, divides, and multiply. Then we have multiple different augmented safe sets, each of which contains 37 instructions, for a total of 91 instructions in a minimal SynthCT safe set. The key takeaway I want to highlight here is that we can implement 75% of the instructions in the ISA using a small set of 25% of the safe instructions. Next, we compare SynthCT safe set to the set of instructions experts believe are safe on today's microarchitectures. So in this Venn diagram here, I show you SynthCT safe set in green, and in blue, I have the safe set, the expert on safe set, which is taken from libftfp, our prior work. We find that a majority of the instructions overlap with the expert written safe set, and this is shown in the intersection. The instructions that are in SynthCT safe set and not what experts believe today are safe is shown on the left side here. This is a small set of instructions that mainly contains division and bit counting instructions, and we believe many of these can be synthesized with some additional effort. And then there are some other instructions that are in libftp safe set and not in SynthCT, and I've just added that for completeness. But the key takeaway here is that there's a large overlap between SynthCT safe set and the set of instructions that experts believe are safe on today's microarchitectures, meaning that SynthCT and its translations may be deployed to harden mostly constant time code for hardware that is in use today. So to conclude, we developed SynthCT to close the security and performance gap in constant time code today. One of our key points in the design is to split the security specification from the implementation of constant time code. We hope that in the long term that our work and many others from the community will encourage hardware vendors to release security-centric microarchitecture specifications and really help software-level tools like SynthCT to harden sensitive code against side channel attacks. Our framework and translations are open source on the GitHub links here, and I'd be happy to talk with you about it offline and take feedback. So thanks everyone for your attention, and now I'll take any questions.
Thank you.